All right, great. So from the last video, now we know what we need to do, how we need to set up reactions in order to make spontaneous reactions or um, make non-spontaneous reactions. Charging versus discharging in a battery based upon the total cell voltage that we get out of our full equation based upon the addition of half reactions, okay? So that's great. So now let's say you're trying to make the world's best, newest, greatest battery, right? Very worthwhile endeavor, very important for the world or whatever electrochemical device that you want to improve. You care about performance. So you want for a battery as high of a voltage as possible, right? So how are you going to maximize voltage? Well, the total voltage of your battery is determined, as we just saw, by the voltage of both of the half reactions. So in a very direct way, the total voltage is dictated by both electrodes, right? Seems pretty obvious. Another attribute that you'd want probably is a very powerful battery, right? And this is power is energy per time, units, standard units, SI units of joules per second, which is a watt, right? Power, energy per time. Power is energy per time. And so there's this kind of speed attribute in power. And so now we went over how a lithium ion battery works. And so if we're talking about a lithium ion battery, the speed is in part at least determined by how fast lithium ions can go in and out of these different anode and cathode materials, right? And just imagine that you have a cathode material that's very, very good. And the lithium ions can go out of the cathode material and come into the cathode material very, very fast. But the anode material, for whatever reason, is not very good. And that is actually the slow step. Your lithium ions cannot move in and out of the anode material very rapidly. The overall power or rate at which you can get the energy out of your battery is going to be entirely dictated by the anode. Who cares if your cathode can do it really fast? Because your anode's slowing it down and they're interlinked, right? So in this way, the maximum power of a battery or any electrochemical device is limited by the slowest electrode. Think about durability, same sort of thing here. You want your battery to be able to cycle 10,000 times. That would be phenomenal without degrading, without losing any sort of energy storage capability, any sort of capacity. Well, if your anode lasts 100,000 times, who cares if your cathode can only cycle 100 times, right? Your durability of your overall battery is only going to be 100 cycles because your cathode is going to fail after that. So your durability, in a very simple way, is limited by your least stable electrode. And this is a problem, okay? This is a big problem that electrochemists have figured out how to optimize for, because the overall performance of any electrochemical device, batteries or otherwise, that we measure is a convoluted combination of the performance of each electrode. And this is really key, okay? And so what electrochemists do is 99% of the time, they're not actually building real electrochemical devices. They're using something, a tool that allows them to best optimize each electrode to then eventually allow others or themselves, engineers, to make better real devices, okay? And the way they do that is through half-cell studies, also called three-electrode cells. These experiments are special experiments that electrochemists do that allow them to study each half reaction individually, and extremely powerful. Because what you can do is you can optimize each electrode, the anode or cathode, make them the best that you can separately, then combine them together, make the best battery, make the best fuel cell, whatever it may be, okay? So we're going to use something called a three-electrode cell to do this. Three-electrode cells enable the evaluation of one half reaction independent of the other. The three electrodes are going to be the following. They have special names. The first is called the working electrode. The working electrode is the electrode undergoing the half reaction being studied. So that could be, in our case of the lithium-ion battery, that could be your graphite. That's your anode that you're planning to use in your lithium-ion battery. That could be your working electrode. Or if you're trying to optimize the cathode, the cobalt oxide, it could be cobalt oxide that is your working electrode. And you'll probably, in reality, do 2 separate experiments where your working electrode is both, changes between both of those so that you can optimize both electrodes. When you're done, put them together and make a better battery. And then what you're going to do is you're going to split the voltage and current from the second half reaction between 2 electrodes. And you may know that you can't have a half reaction just in isolation. So let's say I want to study the anode of the lithium-ion battery. Well, the anode is graphite, the anode means oxidation, but I can't just be removing electrons. I can't just be oxidizing without reducing. I still have to do reduction. Anytime there's oxidation, there's reduction. Anytime there's reduction, there's an equal amount of oxidation. You can't just build up charge indefinitely. Okay, so the half reaction that I don't want to study, I'm going to treat very specially. Okay, I want to study the working electrode. I don't want to study the other half reaction, but I need the other half reaction. Okay, so I'm going to study that by splitting up how it works between 2 electrodes. Okay, the voltage is going to deal with one of those. It's going to be called the reference electrode. And the current of that half reaction is going to be mostly controlled by the counter electrode. I'll explain what that means. Second. First, let's talk about the reference electrode. What's the purpose of the reference electrode? That contains a half reaction of its own to set up voltage versus the working electrode. Okay? No current flows through the reference electrode. The reason is because if you flow current through the reference electrode, then you're changing that reaction, right? And it's not a stable reference anymore. So what you want to do is you want to just probe this half reaction, probe what its chemical potential, chemical voltage is, but you don't want to alter it, because if you alter it, then you're changing its voltage. It's no longer stable. You want something stable. And so the reference electrode is staying in chemical equilibrium so that it always has the same voltage. It does not change and is hence stable. Most commonly used reference electrode, there's a bunch that are used, but the most commonly used one is silver chloride in aqueous electrolytes. It uses this equilibrium. Basically, you put a piece of silver wire in salt, and there's an equilibrium between silver chloride precipitates, which are insoluble in water, and silver. It's a very kinetically fast reaction, so it's a very good thing to probe. You don't have any lag in your system because the reaction's slow, and that's very good. And again, we're not going to pass any current here in the reference electrode. We're just probing it to help us set up a known voltage at our working electrode. Okay, but if we're just probing it, we're not passing any current. The current has to go somewhere, right? And so that's going to happen at the counter electrode. So the current is going to flow through the counter electrode to compensate for the opposite current flowing through the working electrode. The voltage of the counter electrode is then going to swing, okay, to whatever value needed to maintain that current, needed to do exactly opposite of what the working electrode is used. Usually the counter electrode, you want it to be something very inert, because you don't want the counter electrode to dissolve because you're applying some high voltage to it, depending upon what the working electrode is doing. So usually people use platinum or carbon or other inert metals. All right, so this is where you get to what a potentiostat is. And the potentiostat is what electrochemists use, the instrument that electrochemists use, in order to conduct these 3 electrode measurements. And in a potentiostat, there is the independent variable that you're controlling is the voltage, it's the potential. That's kind of what potentiostat means, okay? Measuring or holding potential. And that's going to be the voltage across the working electrode versus the reference. Remember, the reference helps us set up the voltage. The dependent variable, right? You can think about this as your y-axis and your x-axis. What you're measuring out, your y-axis, is the current that passes through the working electrode. So you end up with a voltage-current relationship where you're modulating voltage and you get out current. What is the potentiostat going to do for you? It has 3 major jobs. The first is controlling voltage across across the working and the reference electrodes. Okay, so it could be modulating that over time, depending upon what experiment you're going to do. Okay, or it could be holding it constant. Right? There's different experiments. We'll talk about those. But it's the second job it's going to do is it's going to make sure that no current goes through the reference. Remember that we cannot have the reference changing. It has to be stable. So we can't pass any current through it. And it's going to direct all that current, depending upon what the working electrode is doing, to compensate for charge buildup on the working electrode through the counter electrode. And so to summarize, I think it's just helpful to kind of draw this out a little bit. And so what we're going to think about is we're going to think about our three-electrode cell. Okay, so we have our, I'm just going to give them abbreviations. We have 3 electrodes in here. There's some solution, right? And I'm going to give them abbreviations. So I'm going to call this W for working electrode. That's what we're studying. I'm going to call this R for reference electrode and C for counter electrode. And so let's say we're doing an oxidation at the working electrode. So we have some, material on here and it's getting oxidized. Okay, so what does that mean? Okay, that means that we're losing electrons, right? So oxidation means we're losing electrons. So coming away from working electrode, gonna have electrons. So there's kind of a buildup of positive charge here. Now, those electrons have to go somewhere, okay? Well, they're gonna go through the potentiostat. And remember what the potentiostat is doing is it's controlling the voltage between the reference and the working. So that's what it's doing. It's saying, hey, working electrode, I'm applying a voltage such that you're gonna get oxidized. So be oxidized. And what does that voltage mean? How powerful is that voltage? Well, that's going to be measured versus the reference. Okay. But those electrons have to go somewhere. Where do those electrons go? Well, they go into the potentiostat and then they come out and reduction occurs at the counter electrode, right? So here, let's say it's a piece of platinum, you're going to have reduction happening. Okay. So what the potentiostat though is physically then doing is there's some circuitry in there and it's controlling the voltage, okay, of the working versus the counter to be whatever it needs to be so that if you have 10 electrons coming out of the working electrode, you have 10 electrons coming into the counter electrode. So depending upon the size and the geometry of the counter and working electrodes, this will not be the same voltage, but just in the opposite direction. It could be something different. Okay, but that's sort of the fundamentals of how a potentiostat works, what it's doing, and how a 3-electrode setup works.